Okay, now for part E, so which is this part here. So we want to find this. Now this is quite different. All the ones we've dealt with so far, they have been of the second order. But here, this is of the third order. You can see here, this is 3 primes here. So what we have there in part E is, so we have y prime 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 plus 3y double prime, then minus 4y prime, then minus 12y equals 0. That's what we have. So the same procedure to solve this homogeneous differential equation. So we're going to form the auxiliary equation. So the auxiliary, anyway you find your y, you replace it with m. So we have m, so this is 3 primes, that'll be 3, then plus 3, we have y, replace it with m, 2 primes, that'll be 2, minus 4, replace it with m, 1 prime, that'll be 1, then minus 12, no prime, that's 0, m to the power 0 is 1, and that equals 0. So the next thing is we solve this equation. So when you solve this cubic equation, when you solve the cubic equation, punch in your calculator. So what you're going to have by solving that is going to be m. I think I have my calculator here somewhere. So you have your m1 equals minus 3. You have your m2 equals negative 2. And then you have your m3 equals 2. Now they are all distinct. They are not equal. Since they are all different, then we're going to use the form that we already know, that y equals c1 e to the power. So since this is different, that'll be negative 3x plus c2 e to the power negative 2x plus c3 e to the power 2x. So using the same form like we have for the second order differential equation. Now we go to the next one, which is f. So for part f, it says we should solve that same one, but then you observe that, let me write that clearly. So we have is, what we have is 16, the fourth derivative of y, the y4 plus 24, the second derivative of y, and plus 9y equals 0. So this is what we really have anyway. So we want to solve this. So in trying to solve this, the same procedure as far as it's the homogeneous linear differential equation. A very good step in trying to solve this is, the first step you take is you form the auxiliary equation. So forming the auxiliary equation, so we said this is going to be 16. So this is y. This is something as, then this is power 4. So we replace it with 4. Then plus 24. So this is going to be our y. Oh, sorry. That should be so we shouldn't write that. That should be m to the power 2, then plus 9 equals 0. So the next thing is we solve the differential, we solve the equation here, this quartic equation. So when we solve that, we're going to have m equals or should I just say m plus, you're going to have m equals 0 plus or minus root 3 all over 2i, root 3 all over 2i. So this is where you have, and where each of them, they have a multiplicity of 2. So we have basically 4 solutions. So the first one is m equals this. So like we have m1 equals I'm writing 0 just for clarity's sake, 0 plus root 3 all over 2i. So we have m2 equals 0 plus root 3 all over 2i, and then we have m3 equals 0 minus root 3 all over 2i, and then we have m4 equals 0 minus root 3 all over 2i. So these two, they repeated themselves, so they have a multiplicity of 2, and then these two, they repeated themselves, so they also have a multiplicity of 2. That was why we wrote it in this form. So I'm going to explain to you why I wrote it in that form, because it's going to be very useful for us. Now we know that normally when you solve a differential equation and then the solution of your auxiliary equation, if it turns out to be y equals alpha plus or minus beta, then beta I, then the general solution should be, that's the general solution of so that this should be m. So the general solution should be e to the power alpha x into c1 cosine of beta x plus c2 sine of beta x. So that's what the general solution is going to be. So but then, and then another thing again that we know is, assuming you solve, maybe this time around probably you're using m star, you solved the auxiliary equation of a homogeneous differential equation, and then you have this form. Probably you had m star equals 2, and then probably 2 has a multiplicity of 2. We said that in such a case, then the general solution is going to be y equals, so you're going to start by writing the first one, c1 e to the power 2x, then plus x c2 e to the power 2x. Then if it was 3, we'll keep on going, it's going to be plus x squared. Then if it was 4, like that, on and on and on and on, as was discussed in class. So this that we have here is a combination of the two. First, it has the form 0 plus or minus root 3 all over 2i, which is of this form. So that's telling us that the general solution of this is going to be of this form, that we should have y equals e to the power, so my alpha here is 0, so e to the power 0x into c1 cosine of my beta. This is my beta here. My beta here is root 3 all over 2. So that's root 3 all over 2x plus c2 sine root 3 all over 2x. So this is it. But this is assuming the multiplicity is 1. But what we have here is the multiplicity here is 2. So since it has a multiplicity of 2, then the solution we have here will be repeated twice, but then with an additional x in the next term. So in other words, the real solution should be y equals, so start with the first one, that's e to the power 0x. So just see how it's being formed. c1 cosine of root 3 all over 2x plus c2 sine of root 3 all over 2x. So this is for the first part. Then we go to the next one, which is going to include x. Then plus x. Then we continue again, x. Then we write the same, the solution again. That's going to be e to the power 0x c1. So not c1 now, we're going to continue by c3 cosine of, that's cosine of root 3 all over 2x. So let's pull this down. Then plus c4 sine of root 3 all over 2x. So this is what we're going to get. So in full, we have y equals e to the power 0x is 1, so that's going to be c1 cosine of root 3 all over 2x plus c2 sine of root 3 all over 2x, then plus x into, so we have c3 cosine of root 3 all over 2x plus c4 sine of root 3 all over 2x. So that is going to be your final solution. That's going to be your final solution of the whole thing. Okay, we're going to look at another example which is quite similar to this, just to ground understanding, and which is going to be part F. So we've done F. Okay, which is going to be part G. So part G is of the form we just dealt with, and it's also an initial value problem. So we have y prime prime minus 2y prime plus y equals 0. We're giving the initial conditions y at 0, 5 and y prime at 0 to be 10. So I'm going to write that down here just for quick reference. So what we have is, which is G. So we have our G to be y prime prime minus 2y prime plus y equals 0, and then we're given the initial conditions y of 0 equals 5 and then y prime of 0 to be equal to 10. That's what we're given. So the first thing is, you want to solve a differential equation. Now the first thing you need to check is it homogeneous? If it is homogeneous, and then what you have here, they are constant coefficients here. The first thing you think of is form an auxiliary equation. So you have the auxiliary equation there. So you solve. Forming the auxiliary equation is going to be m squared minus 2m plus 1 equals 0. So when we solve this, it's going to be m minus 1 squared equals 0. And then this implies that the solution is going to be m equals 1. So where the multiplicity is the power here. This is what we've been talking about. So the multiplicity is 2. So since the multiplicity is 2, then that implies, like we did earlier on, the general solution, which is going to be my y, is going to be c1 e to the power 1x, then plus, so we're going to go again, since we are going, the next step is going to contain x, then c2 e to the power x. So this is going to be our solution. But then we observe that it must satisfy this condition and then this condition. So starting with the first condition, that is y at 0 equals 5. So when x is 0, y is 5. So y is 5 when x is 0. That's c1 e to the power 0, which is 1, plus 0 times this, which is 0. So I already have a value for my c1. So this implies that y equals, so c1 equals 5. Now it becomes 5 e to the power x plus x c2 e to the power x. Now the next thing I want to find is, it said the derivative of y at 0 is 10. So let's find derivative of y. So the derivative of y is going to be 5 e to the power x plus, we apply product rule here. So what we have is going to be c2 e to the power x plus x c2 e to the power x. So and then we are told that at 0 the value is 10. So 10 when x is 0, that's 5 plus c2 plus that. So this implies, from here it implies that c2 equals 5. So since c2 equals 5, then we have now this as our final solution. So the final solution of what we're doing here now using this is going to be y equals 5 e to the power x, then plus x times c2, which is going to be 5x e to the power x. So you could either leave the answer like this, or you just say y equals, so since 5 e to the power x is common, so you have 1 plus x. So that is going to be the general solution of that differential equation.